So my original plan for today was to talk about my own research, but to be honest, I didn't really feel like it. So if you want to know more about my research, there's a great video that you can watch on my webpage. That is a talk I gave at Jane Street um, last January, I believe. I'm really lucky that they produced a good video of the talk. So if you're interested in my research, you can go watch that. I also have other videos and lots of blog posts and papers and so forth. But today I was thinking I would talk about something else. So all quarter, I've been referring you to papers and additional reading material and some of the topics that we've just been discussing. And some of them I've mentioned by name and some of them I haven't. But I thought that I would go through and pick out a handful of papers that I think are interesting. And I had a kind of fun experience this weekend going through and looking for primary sources on some of the topics that we've discussed. And I actually had some interesting discoveries, which I'll try to share with you. So the first thing that I want to talk about actually is, so I want to come back to this this great illustration that Chris Callahan shared in his talk a few days ago. So he drew a picture that looks something like this. So at the top, there was something called two-phase commit, which we haven't really discussed, but we'll talk more about that in a second. And then Paxos, or Raft, or any other consensus protocol, typical consensus protocol goes here. After this was something called PBFT, which we didn't talk about in any detail either, so I'll talk a little bit more about that. And at the bottom of this, he put blockchain consensus. And I'm going to put consensus in quotes here, because as Chris discussed, it isn't really consensus. So the idea is that as you get lower on this diagram, on this arrow here, you get slower and more fault tolerant. I should also add slower and more expensive to implement. So out of all these things in this picture, the only one that we had really talked about was Paxos. So I thought we would fill in a few of the gaps here. So two-phase commit, or 2PC as it's sometimes known. So Chris put this here. I might have put primary backup or chain replication in this spot. So let me talk about why. So two-phase commit is a protocol where if you have a bunch of replicas, you have a coordinator, and the idea is that everybody needs to come to a decision about whether to abort or commit some transaction. So this is typically used in a database setting where you have transactions. The coordinator goes out and asks everyone if they want to abort the transaction or commit the transaction. So why would a replica want to abort a transaction when other replicas want to commit it? Well, it could be something like that replica and only that replica doesn't have enough disk space to commit the transaction, something like that. So the coordinator goes out and asks everyone if they want to abort or commit. And they actually all have to say commit. So this isn't a situation where the majority wins. They actually all have to say commit. When they all get back to the coordinator, it'll tell everybody what the decision is. So if they all said commit, the coordinator will tell everybody, okay, commit. And if not all of them said commit, the coordinator will say abort. So the point is, a coordinator is needed. So this is similar, actually, to primary backup or chain replication. In the sense that if you want to do it, you need somebody, and if you want to do it and you want it to be fault tolerant, you need to have some sort of coordination. So you could do these things with only one coordinator. but you wouldn't get any fault tolerance, right? And as we've discussed, if you want to have fault tolerance, then ultimately you're going to be dependent on having some sort of consensus protocol, right? So we talked about how there are different ways to replicate a bunch of state machines, right? If you use something like primary backup or chain replication, then the coordinator process, in order to not be to not fail completely if the coordinator dies, you really need a cluster of processes that are all working as one, and those processes need to be running a consensus protocol among themselves. Alternatively, you could use something like Paxos or Raft to do state machine replication over all of the processes, over all of the replicas, and have them coordinate directly with one another instead of having a coordinator process. Either way, you're dependent on a consensus protocol if you want to be tolerant of failure. So in this picture, this was actually a good, I think in some ways this was a good choice to have at the top, because two-phase commit is typically not fault tolerant in the sense that there typically is only one coordinator. So you might ask, well, given that two-phase commit is something that you might want to do, why don't we have a coordinator? Like, or why don't we have a cluster of processes that behave as the coordinator instead of just having one? Why don't we get rid of that single point of failure? So, and why don't we use a consensus protocol for that? So that, in fact, has been done. So that's the first paper that I want to mention to you. It's a classic paper, so I have a whole bunch of browser tabs here that I want to share with you. So the first one here is this classic paper called Consensus on Transaction Commit from Jim Gray and Leslie Lamport. I think this was from, I want to say, is there a date? 2006. Okay, yeah. Note what they say here. So they say, I'll make this a little bit bigger so people can read. The classic two-phase commit protocol blocks if the coordinator fails. So that's what we were just talking about. The coordinator is that single point of failure. The Paxos commit algorithm, which is what this paper is about, runs a Paxos consensus algorithm on the commit abort decision of each participant. And then they say, so F in this case is the number of coordinators that can fail. So they say there are two F plus 1 coordinators, and F of them can fail. And they say the classic two-phase commit algorithm, in other words, the thing that that Chris was talking about when he put 2PC on that picture, the classic two-phase commit protocol is the special case of Paxos commit, they claim, where F equals 0. In other words, where no coordinators can fail, because there's only one. So I think this is interesting, right? They're taking Paxos, the consensus protocol, and plugging it into this transaction commit problem and saying, okay, well, if you want to make transaction commit fault tolerant, just run Paxos. And so that's very analogous to what we talked about in the idea of having a cluster of coordinators running a consensus protocol, and that cluster of coordinators behaves as a single coordinator for something like primary backup or chain replication. So one thing that you'll find as you look at the literature on consensus is that, and this kind of became clear, I think, in Chris's talk a little bit. So when he was talking about all of these alternatives, let me go back to this here. Two-phase commit, Paxos, PBFT, blockchain consensus. He was talking about them as ways to do replication. So you might think, oh, well, Paxos isn't a way to do replication. It's a consensus protocol. But the thing is, those two things are really inextricably linked. And one of the most common reasons to use a consensus protocol is to do replication. So, so these things really are all, they really all do belong in that category of techniques for doing replication, in the sense that replication requires the processes to agree and to come up with an agreement on the order. So whether you do that by having a coordinator who tells everybody what the order is, or whether you do it by having those processes all run Paxos, both of those require agreement. And if you want it to also be fault tolerant, if you're doing it in the way of having a coordinator, then that coordinator ultimately ends up having to actually be a cluster. So, okay, so that's what two-phase commit is. A coordinator goes out, asks everybody if they want to abort or commit. They all have to say commit. So it's not a matter of majority vote. And then the coordinator tells everybody what the decision is. Okay, so that's two-phase commit. We've talked about Paxos. What about PBFT? So this stands for Practical Byzantine Fault Tolerance. So this is another classic paper from 1999. This is the work of Miguel Castro and Barbara Liskov. Liskov is a legend in distributed systems, also in the field of programming languages. She developed a lot of the fundamental theory behind object-oriented programming, and these days her work concentrates on distributed systems and especially Byzantine fault tolerance. So I'm going to be honest with you. I do not know PBFT well enough to teach it. Maybe in the future I'll find a way to incorporate it in this class. This is not the year, but I wanted to talk to you about it for a second. So despite practical in the name, PBFT isn't typically used in practice that often. It's a replication technique that tolerates Byzantine faults. And you know, you can look at this paper if you're interested. But just to talk a little bit about the characteristics of it. So in PBFT, the property that it has is that n minus 1 over 3 out of n replicas can fail. Fail simultaneously. So fail in this case, what does fail mean? Well, fail doesn't just mean crash. Fail in this case means have Byzantine behavior. So a process with Byzantine behavior could be pretending to fail. It could have actually failed, or it could be pretending to fail, or it could actually be malicious, right? It could be it could be sending wrong information to other processes. So what does this mean? It's actually floor of n minus 1 over 3 is the number of replicas that can fail. So let's think about what this would mean in a real system, okay? So let's say you had 3 replicas. Well, if you had 3 replicas, so if n is 3, then let's see, 3 minus 1 is 2, 2 divided by 3, floor of that is 0. Okay, so no replicas can fail if you have 3. Okay, so that's out. Similarly, if you had 4, what would happen? Okay, 4 minus 1 is 3, 3 divided by 3 is 0. Yeah, okay, so you can't have 4. It turns out that 5 is the minimum number of replicas that you can have in PBFT if you want it to be possible for 1 to fail. So this would seem to make sense, right, just intuitively, right? So we saw that with Paxos, for example, Paxos can work just fine if you have 3 acceptors and one of them fails. It'll still work. because 2 out of 3 is still a majority. So if one of them has failed, and in that case, we're just talking about crash failures and omission failures, not Byzantine behavior. But 1 out of the 3 can fail. If for PBFT, if you want to have any fault tolerance, you need to have more replicas. And this would seem to make sense because it's a stronger notion of fault tolerance that we're discussing here. So this isn't typically done in practice because in order to get the fault tolerance, you need more replicas, which means more money, and replication is slower, and it's a bigger investment for a kind of fault that doesn't necessarily happen very often, depending on the particulars of the system. It's great when you need it. And this paper was influential because previous Byzantine fault-tolerant replication strategies were slower than PBFT. And so PBFT has the advantage that it's faster than other known techniques for Byzantine fault-tolerant replication. But it's still not as fast as not using PBFT. So, but I felt like I ought to mention it because it is a step in this picture here on the way to blockchain quote-unquote consensus. So hopefully that fills in some of the gaps for you in this picture. And I think if you took one thing away from Chris's talk, it's that everything in distributed systems is a trade-off, right? As you get lower in this picture, you get more expensive to implement, not to mention when you get to blockchain consensus, you get more expensive in terms of actually running it, right? More expensive in terms of the environmental impact on the world, and slower for sure, but also more fault tolerant. And I don't know, I mean, putting consensus in quotes here is, I say that because as we talked about in Chris's talk, with Paxos, or with, and even with PBFT, there's a point at which you know consensus has been reached and there's no going back from it. With blockchain consensus, that's not the case. All you have is a sort of probabilistic guarantee as time goes by. So it's not the same kind of guarantee that consensus has been reached that you get with these other consensus protocols. So as Chris said, you should be very careful about deciding to use this for consensus. And most of the time, you probably won't need it. Most of the time, you don't even need PBFT. And honestly, a lot of the time, you don't need Paxos. So that's something that we've tried to emphasize in this course. Try to use the weakest thing that you can, right? If you can get away without having strong consistency among replicas, then maybe that's a good choice. Or maybe you can do some hacks to make it so that replicas agree even if the order of messages isn't the same. And so that's something that we began to talk about with the discussion of conflict-free replicated data types last time. Okay, so hopefully I filled in a couple of the gaps there. I went back to the beginning of the course and started to think about all the things that we've talked about. And so one kind of question that came to mind, going back way to the beginning when we started to talk about logical clocks. So I wanted to know who, I told you guys that vector clocks were invented by a couple of authors independently. So and I decided to go back and fact check myself on that. So to remind ourselves about vector clocks, first let's remind ourselves about Lamport clocks. So the next paper that I have here is the undisputed classic time clocks and the ordering of events in a distributed system. This was from Leslie Lamport in 1978. And what I hear people say about this paper is that this paper was one of the first papers that really treated distributed systems as a science as opposed to just a sort of collection of tricks or heuristics. So this is the paper that introduced the concept of happened before, which we've spent so much time talking about in this class. So we can actually dig in. And by the way, so if you look at these pictures here, so these are among the first Lanport diagrams, which we've been discussing all quarter. Notice that when Lamport draws them, the arrows actually go up, which is kind of funny. So time goes up in these pictures, which to me makes them harder to read. I like to do time going downward. And authors do these all kinds of different ways. Sometimes you'll see time goes left, time goes right. It varies. Lamport is actually the only person I've ever seen who makes time go up in his Lanport diagrams. Notice also that he makes the choice of drawing these wavy lines to kind of emphasize the uncertainty of the system, which is kind of funny. But anyway, so right here is the definition of the happens before relation, which we've discussed. And you can go read this paper if you want to. It's not very long. Let me give you just a brief tour of the paper. So the beginning part of the paper, it introduces this notion of happens before. And then he starts to talk about Lamport clocks. This section, logical clocks, defines Lamport clocks, where recall that a Lamport clock is just a number rather than a vector of numbers. So it's a way of assigning a number to an event, as he says. And here's the property that we talked about, which he calls the clock condition. So for any two events, A and B, if A happened before B, then the Lamport clock of A is less than the Lamport clock of B. And then he points out, note that we cannot expect the converse to hold. So that's what we talked about, as opposed to vector clocks, of course, where we said that it's true both ways, right? But he doesn't actually invent vector clocks in this paper. That happened later. Now, he goes on in this paper to use this notion of, so as you know, before I get to that, so Lamport clocks give you a partial order on events. And then he says, well, okay, what if you wanted to turn that into a total order? So he says, okay, well, you can just use the partial order, and then if, let's say, two events have the same Lamport clock, like two events both have the Lamport clock of 4, then you just use some arbitrary ordering to break the tie between processes. Like, for example, if the processes have numbers, like you have process 1 and process 2, and they both have an event with the Lamport clock of 4, you just arbitrarily say that events on process 1 happened before events on process 2. So that's what this says here. We use any arbitrary total ordering of the processes. There's nothing deep going on there. We're just saying just pick any total order that is consistent with the partial order. So then he goes on to say, okay, we're going to try to define, well, there's somewhere in here, let's see, where does it start? You can see I'm real practiced here with this lecture. Yeah, so there's a discussion of this idea of implementing a distributed mutual exclusion algorithm. Let's see, I can't find where that part of the paper starts. Let me find it. Yeah, okay, oh, right here. We will illustrate the use of this total ordering events, which we just came up with arbitrarily, by solving the mutual exclusion problem. So this is the problem where you have some resource that a bunch of processes are supposed to share, and only one of them is supposed to have access to the resource at a time. And so you need to find some way to ensure that exactly one has access to the resource at a time. Now, nobody actually uses Lamport's mutual exclusion algorithm that's laid out in this paper because it's not fault tolerant. So although it's a nice exercise and a demonstration of the use of Lamport clocks, it turns out not to be actually particularly practically useful. But it's interesting to look at. And this, as I said, this paper was very early in the development of distributed systems, so there weren't a whole lot of people thinking about this right now. And then he goes on and introduces and starts to talk about this concept of state machines. And notice he mentions each process independently simulates the execution of a state machine. And so this is kind of hinting at what people would see later with state machine replication and so on. And then at the end of the paper, he starts to try to go back to this notion of physical clocks. And I really don't know, I'll tell you the truth, I don't know what he's talking about in this part of the paper. It doesn't make sense to me. I think you would have to be a physicist to understand it. And I don't even know if physicists understand it. Feel free to read it yourself. But I wanted to share this paper with you because it's a classic. And it's probably Lamport's most cited paper. So this doesn't answer our question of who invented vector clocks, but it gives kind of a lower bound, right? So this was the notion of Lamport clocks, which predate vector clocks. So 1978 was when this paper came out, and vector clocks were soon to follow. So in some sense, you know, maybe it doesn't really matter who invented vector clocks, right? Because the idea kind of, we know that the idea arose independently in a number of different settings. So here's the paper that I did recommend reading about vector clocks. So this was not one of the primary sources on vector clocks. This is a paper that came later in the 90s. So this is the Holy Grail paper that I recommended in class. I do recommend reading this if you want to know a whole lot about this idea of detecting causal relationships in distributed systems, in distributed computations. So it starts to talk about like what would happen if you used Lamport clocks, and then here's an example of how just using Lamport clocks is insufficient. So let's use vector clocks instead. Are vector clocks actually the best solution? And then some discussion of that. So they have an interesting footnote in here where they say the concept of vector time, meaning vector clocks, cannot be attributed to a single person. Several authors reinvented time vectors for their purposes with different motivation and often without knowing of each other. And then he mentions a few citations from the distributed database world. But then two papers are mentioned in particular as being a generalization of Lamport clocks, 17 and 44. So these are the ones that I mentioned to you, which were Matern and Fidge. So let's talk about these. So the Fidge paper was from 1988. And here it is. So I had to dig this one up. It was actually a little bit hard to find online. Or it was hard to find an authoritative version. I ended up finding this version from a course taught at Yale. I wasn't sure where to find a version that was like an author-hosted version or something that was hosted on some official repository of papers. I always try to share official versions of things when I can, because sometimes the other versions don't necessarily, you don't know that they're going to remain online and so on. But this is the best I could find for this one. So in this paper, he ends up inventing vector clocks. He doesn't call them vector clocks, but he makes this interesting point here, which is that so with Lamport clocks, you can take them and you can use the Lamport clocks and then extend that partial order to a total order. But then he points out this only yields one of the many possible and equally valid event orderings defined, and it's more useful to have access to the entire partial ordering. And notice that there's, so he says, this paper presents an implementation of the partially ordered relation happened before that is true for two given events, if and only if. Importantly, this is an if and only if here, not just an if the first could causally affect the second. So that's the both ways of the of what Lamport called the clock condition. So let's just write that down again. So A happened before B if and only if the vector clock of A is less than the vector clock of B. And that is what Fidge is talking about there with that if and only if. So who invented vector clocks? Well, it could have been this guy, Fidge, Colin Fidge in 1988. Okay, well, what about the others that we talked about? So, and if you go on and read this paper, it's interesting. I'm not going to go any further into it than this. Here's the other one that was cited in that Holy Grail paper as one of the people who extended the idea of Lamport clocks. Actually, I guess there was one other thing that I wanted to talk about in the Fidge paper. So if you go to page 3, yeah, okay. So just to prove to you that this is where it's actually discussed. Okay, so rather than a single integer value, timestamps are represented as an array with an integer clock value for every process in the network. So there it is. Looks like vector clocks to me. Okay, so here's somebody else who might have been the inventor of vector clocks or who simultaneously invented vector clocks. So this paper, Virtual Time and Global States of Distributed Systems by Friedman Matern. So if we look, let's see. There's some part where he starts to talk about, yeah, okay, here we go. In this paper, we aim at improving Lamport's virtual time concept. And so he points out that vectors is a natural representation of time in a distributed system. And then what I think is interesting is that starting in section 3, he begins to talk about the concept of consistent cuts, which we talked about in the context of the Chandy-Lamport algorithm, which actually predates this. But what's interesting is that in the Chandy-Lamport algorithm, so at the time that was invented, we didn't have vector clocks yet. So there wasn't, so in this paper, Matern is actually tying together this notion of consistent cuts, and notice, like, it's exactly the idea that we talked about in class. So we said a cut will partition a set of events into past and future events. So a cut is a line that goes across the process lines here, dividing it into past and future. And then we have this property that we discussed in class, where a cut is a consistent cut if an event's in the cut, then everything that happened before that event happened too. So that's what this says. And then there's an example of an inconsistent cut. Notice again that this is one of those sideways Lanport diagrams. So in this one, time is going to the right. Okay, so we'll come back to this this idea of snapshots in a little bit later. But one thing I noticed as I was kind of spelunking through these old papers to find, who invented vector clocks. Well, I also looked at some textbooks, and so here's one that I looked at. So I noticed that these people said, the system of vector clocks was developed independently by Fidge, Matern, and Schmuck. So I didn't know who Schmuck was. So I thought, okay, well, I'd better go look up this Schmuck person so I can figure out, who that is, and maybe that person it also simultaneously invented vector clocks. So I go to look at this up. His name is Frank Schmuck, and he was a PhD student at Cornell in the 80s. So the thing that's being cited here, citation 23, is actually his PhD thesis, which is interesting, right? Because these other people were all established researchers when they published this stuff, but this was in his thesis. It didn't even appear in like a peer-reviewed paper. So so I had to go dig up Frank Schmuck's PhD thesis to learn more. And this was a little bit hard to find online as well, but I found it. So here is Frank Schmuck's PhD thesis from 1988. The use of efficient broadcast protocols in asynchronous distributed systems. He worked with Ken Berman at Cornell. And so, okay, here we are. It's like this 137-page document. And I wanted to dig into here to think, okay, well, apparently he independently invented the notion of vector clocks somewhere in here. How am I gonna find it, right? So I go in here and I'm like, okay, well, like you can kind of start scrolling through, and there's like some front matter, right? Like okay, here's like the abstract, and then there's going to be like some biographical sketch. All right, we can learn more about Frank Schmuck. There's a dedication to his parents. Here's where he acknowledges his advisor and his family and friends, and so on. Okay, now we're getting into the good stuff. But I'm like, okay, this is going to take way too long. So let's just search for the word causal, right? Hopefully if we search for causal, we're going to start to find a discussion of vector clocks. All right, so we start to go through. Okay, this is promising, causal broadcast. Okay, so we start to get to something that's sounding good here, based on the idea of potential causality introduced by Lamport. Okay, so that's sounding promising. Okay, causal broadcast also respects FIFO ordering. That's sounding like stuff that we've talked about. But I still don't see the part where he actually invented vector clocks. Let's keep looking. We're still only on page 28 of the whole thesis. Keep looking. Causal ordering, blah, blah, blah. Okay, here we go. Causality and timestamps. This is starting to look promising. Okay. Okay, we're starting to talk about messages that have timestamps attached to them. What do those timestamps look like? I found this earlier, but I'm just gonna jump ahead. Okay, here we go. Here it is. So here's where he defines his notion of timestamps. A timestamp is a vector of integers, where the entry for a given process, the index in that timestamp for a given process, is the number of events on that process. And then he goes on and talks about how you can compare timestamps and so on. And so there's a discussion up here. So Lamport introduced logical timestamps. We can generalize this idea to timestamps which are vectors of integers. And here, tantalizingly, there's a citation. SCH85. This is so SCH are the first three letters of his name. So this is a self-citation. So he's citing his own work. But if we go and look at SCH85, F. Schmuck, Software Clocks and the Order of Events in Distributed System, unpublished manuscript, November 1985. Okay, so he's claiming that in 1985, he invented this idea of extending the single number logical timestamp to a vector of numbers, but he never published it. So he's saying that he did this in November 1985. We kind of just have to believe him. But note also that there was a footnote here, footnote 2. Okay, what does that say? And then, this is fascinating to me, the idea of vector timestamps was developed independently by Ladin and Liskov in 1986. So I was like, okay, what's Barbara Liskov, really? Did she invent timestamps? So, so this was really interesting to me. So I go and look up this citation, LL86. So that turns out to be this paper by Barbara Liskov and Rivka Ladin, two women, I might point out, from 1986. So this is a paper called Highly Available Distributed Services and Fault-Tolerant Garbage Collection. And Schmuck cited them for having invented vector timestamps or vector clocks in 1986. So this paper is about distributed garbage collection, one of the hardest problems in distributed systems. I'm convinced that it's basically impossible. So if you go through, it turns out that the term that they use for, I looked through this previously, so otherwise I wouldn't know this, but the term that they use for vector clocks is multi-part timestamps. So here's a discussion of timestamps. Multi-part timestamps, where there is one part for each replica. Thus, if there are n replicas, a timestamp has parts that are integers for 1 through n replicas. And then they also point out, since there will typically be a small number of replicas, e.g. 3 to 7, using such a timestamp is practical. And then they go on and talk about how you update timestamps, how you merge timestamps, and so forth. So this was yet another place where this idea of timestamps arose. So going back to our list here, so we had Fidge and Matern, who both published their papers in 1988. There was Schmuck, whose thesis came out in 1988, but who cited himself having done this in 1985. And then there's Liskov and Ladin from 1986. So I find this interesting, right? Because I always hear these three names, or I always hear these two names mentioned. And then sometimes this name gets mentioned, but I never hear these names getting mentioned to answer this question of who invented vector clocks. So I might do a little bit more digging on this, but I might end up having to write a blog post about this. Okay, so cool. So I learned something new this weekend about the history of distributed systems. All right, so we're up to the late 80s by this point. I mentioned that Schmuck was a student at Cornell, and he was working with this guy Ken Berman. So there's a really wonderful Berman paper. So I kind of skipped over some stuff in Schmuck's dissertation about causal broadcast and so forth. So my favorite paper on that topic is this one by Ken Berman and his collaborators called Lightweight Causal and Atomic Group Broadcast, or excuse me, Atomic Group Multicast. So it's about this system that they built at Cornell called ISIS. The name of it didn't really age well, but there's some interesting distributed systems ideas in this paper, and so there's a discussion of causal broadcast, which we also discussed in class. So I want to talk about that a little bit. So let's see. So when we talked about causal broadcast, let me actually bring up the relevant parts of this paper. So first, there's a discussion of vector clocks. I'm going to skip ahead the early stuff in the paper, which talks about ISIS and the ISIS system. And then there's a whole bunch of like kind of introductory stuff and the system model and so forth. I'm going to skip past all of that and go to the part of the paper that starts to talk about vector clocks and then causal broadcast. So let's see, waiting for it to load. Okay, so here we go. So, whoops, I guess we went too far. Okay, so section 4 of the paper talks about vector clocks, or section 4.3 actually. So this is exactly what we talked about in class when we talked about vector clocks. So if you have a process at the start of execution, it has a vector clock of all zeros. Every time you do a send, its position in the vector clock gets incremented. Messages have vector clocks piggyback along with them. And when a process receives a vector clock, it gets merged with its own vector clock. And then that ends up being the foundation of how they implement causal broadcast, which is discussed in the next section. So this CB cast here, which is what most of this paper is about, stands for causal broadcast. So here's the causal broadcast algorithm that's in this paper. Right here, starting at where it says the protocol is as follows. So before sending a message, you increment its vector clock, and you timestamp the message with the vector clock. Here's the key part. When you get a message, you don't deliver the message yet. Delay delivery of the messages until until this is true. So you have to make sure that you have to make sure of two things. One, you have to make sure that the received clock is 1 bigger than the local clock in the sender's position. That's what this first part says. And then you have to make sure that the received clock is less than or equal to the local clock in every other position. And that's what we talked about in class. So this is what they said. Now, then they say, okay, when a message is delivered, when those rules are met and you get to actually deliver a message, then you update your local clock in accordance with the vector time protocol that was previously discussed. So what we said when we talked about causal broadcast is we said when you deliver a message, you just increment the local clock in the sender's position. What they said is just use the standard vector clock thing of merging the local clock and the received clock and take the pointwise maximum of the two clocks. So that's what they say here when they say vector clock is updated in accordance with the vector time protocol. They say do the usual vector clock thing of just merging the clocks. It turns out that these are equivalent, actually. So some people asked, when we talked about causal broadcast in class, some people asked, why aren't we going to merge these clocks? Don't we have to merge the clocks? So it turns out that these are equivalent because of the conditions on when it's safe to deliver a message. So because it has to be the case that the received clock is bigger than the local clock by 1 in the sender's position, and also every other position has to be less than or equal to the local clock, it turns out that merging the clocks and just doing this increment the local clock in the sender's position, it turns out that these two things actually result in the same thing. So like just for example, like if you had the clock on, if your process had the clock, I don't know, 1, 4, 5, and you receive a clock. So let's say that your let's say these entries are like for processes A, B, and C respectively, and your process A. And let's say that you receive a message from process B that's something like I don't know, 1, 5, 3. So you get a message from process B with this clock. So the way that we talked about causal broadcast was we said you increment the local clock in the sender's position. So that would leave you with 1, 5, 3. Or excuse me, it would leave you with 1, 5, 5. So that's what you would get if you incremented the local clock in the sender's position. But if you just merged the clocks according to the pointwise maximum, then you also get 1, 5, 5. So these two things do the same thing because of the conditions on when it's safe to deliver. This one happens to be safe to deliver because it meets those criteria of being one big than the local clock in the sender's position, because it came from process B. And it's less than or equal to the local clock in every other position. And the 1 here is less than or equal to 1, 3 is less than or equal to 5. I don't know where I learned my version of this algorithm, the version where you just increment the local clock in the sender's position. In retrospect, it seems like a kind of an obvious optimization, right? Like if you can just increment a number and then have that be the same as what you would get if you were to actually take the maximum of all these numbers, then why would you not do that, right? Why would you not do the thing that's easier to compute? But I don't remember where I learned my version, and it was interesting to look back at this Berman paper that introduced this idea of causal broadcast, and to see that they actually didn't do that optimization of just increment the local clock in the sender's position. At least I don't see anywhere in here where they talk about that. So I don't know where I learned my version. I didn't invent it. I learned it somewhere, but I don't remember where. And so if anybody knows where that came from, let me know. Okay, so we're up to the 90s now in our little tour through history. I'd like to keep going. I may not get through actually all the papers that I wanted to get through. Let's see. Let me pause at this point and look at chat and see what questions people might have, if any. Yeah, so there's some good comments here. Yeah, somebody's pointing out the work on communicating sequential processes. Yeah, from Hoare. Yeah. So this was great foundational work on concurrency. I came to distributed systems from programming languages, so my background is much more to do with this reasoning about concurrency from programming languages point of view than from a distributed systems point of view. These days, I'm excited about distributed systems because the questions of fault tolerance aren't necessarily discussed so often in the PL setting. I get excited when a PL paper does discuss those things, and I'm actually really interested in the intersection of these areas. But yeah, the CSP work was incredibly important and foundational. And yes, I also feel a little bad for Frank Schmuck for having the last name Schmuck. It's kind of unfortunate. All right, moving on. Okay, so I was going to say a little bit more about snapshots, but I think I just want to share one really nice thing from this paper. So this was the Chandy-Lamport algorithm. This is the paper that introduced the Chandy-Lamport algorithm in 1985. And there's just a beautiful quotation in here that I want to share. I don't actually recommend this paper as a way to learn the algorithm. I think this paper is hard to understand. But I want to share this quote because I think it's really lovely. So they describe their algorithm as a state detection algorithm. So what they're trying to do, if you recall what a snapshot is, it's trying to understand the global state of a distributed system. And trying to get a coherent overall view of the state of a distributed system. So they say the state detection algorithm plays the role of a group of photographers observing a panoramic dynamic scene, such as a sky filled with migrating birds, a scene so vast that it cannot be captured by a single photograph. The photographers must take several snapshots and piece the snapshots together to form a picture of the overall scene. The snapshots cannot all be taken at precisely the same instant because of synchronization problems. Furthermore, the photographers should not disturb the process that is being photographed. So we talked about that, right? We talked about how the Chandy-Lamport algorithm can run at the same time as the application that it's snapshotting. For instance, they cannot get all the birds in the heavens to remain motionless while the photographs are taken, yet the composite picture should be meaningful. The problem before us is to define meaningful and then to determine how the photographs should be taken. So I find this analogy really beautiful and really nice in trying to understand the challenge of trying to snapshot distributed systems. You can't take a picture of every process at the same time because there is no global notion of time. Um, and, and you certainly can't get all the birds to hold still. So, or if you did, you know, if you could, in fact, so you certainly can't get the birds to hold still, right? You could actually pause all the processes in a distributed system, but you really would like to avoid that if at all possible. So I think this is a really lovely quotation that kind of describes what they're after here. Okay, moving on to a different topic. So after we talked about vector clocks and causal broadcast and consistent cuts and snapshots, we started to talk about replication in this course, right? And the first replication strategy that we talked about was primary backup. If you go and look and you try to find, okay, who is the first to come up with primary backup? This is the paper that tends to get cited by Alsberg and Day. This was from the 70s. Let's see if there's a date on here. Okay, 1975. So this is the paper that you always find cited. I started to look through here, and it didn't seem to feel to me like it was particularly close to what we think of as primary backup replication today. I believe that these guys were first, but I wouldn't necessarily recommend this paper as a way to learn what primary backup replication is, because it doesn't look a whole lot like what I now think of as primary backup replication. Nevertheless, I think it's important to mention it, to point out that primary backup replication is an old idea. Notice that they're motivating this idea of replication so first of all, notice, okay, the development of large packet switched networks, as opposed to circuit switched networks. You know, packet switched networks where packets can be lost and where availability is an issue, right? It's a challenging environment to work in. And so they're motivating it by talking about these pre-internet networks like ARPANET. So these were the old days, right? And so it's very interesting sometimes to read these old papers and just think about the perspective that they had, and then think about how well did this hold up with the way that we think about these things today. And often, you know, like some of the assumptions that they made are surprisingly still make sense today, and you can really admire the authors for having such an amazing vision. Other times, the assumptions that they made don't make sense at all today. So this is who you see cited for inventing primary backup. I wanted to point out some work that's a lot more recent and closer to home. So here's a paper from our own UCSC. This has to do with the Ceph system. Ceph is a distributed. Some people call it a file system. Some people call it an object store. So it's a distributed storage system. And I wanted to bring this up because there's a nice illustration in here of what they came up with, which is kind of a hybrid of primary backup and chain replication. So there's this really nice figure here in this paper from 2007 about the replication strategy that they came up with that kind of merges primary backup and chain replication. So the first part here, so primary copy, this is a synonym for primary backup. If you see people talking about primary backup, or if you see people talking about primary copy, that means the same thing as primary backup. So this should look familiar to you. We've talked about primary backup already. Both reads and writes go to the primary. The primary is this one right here. OSD is a notion that's specific to Ceph, which is what this paper is about, but just think of it as a replica. And then this over here is the client. So both reads and writes go here. Notice that there's a delay because the primary has to go out and talk to all the backups, wait for them to acknowledge it, and then get back to the client. Chain replication which we've already talked about. The primary passes writes on to the backups, and then the tail of the chain acknowledges the client. What they came up with, which is kind of in some ways a combination of the two, is what they call splay replication. So in splay replication, the writes go to the head of the chain, but then the head of the chain in parallel sends the update all out to everybody else. And then each of those has to acknowledge the tail. So the delay is incurred. There's still a bit of delay, right? So delay is incurred at the tail here between the time when the tail gets this right and the time that it gets these messages. And that right there is the commit point. So this, what they call apply write in this picture, is what we called commit point. Well, I guess they're talking about applying the write on all of them. So I guess we should think of, so this one here is the commit point for primary backup. This one is the commit point for chain replication, and this one is the commit point for splay replication. So there's a little bit of a time savings here, because these messages from the primary get sent out in parallel to all of these replicas, and then the tail acknowledges the client, just like with chain replication. So according to them, this helps minimize write latency. So I think this is kind of interesting that even in 2007, people were still coming up with new ways to improve strongly consistent replication strategies, and they're still coming up with ways to do it today. Okay, so there's that. All right, so that's it for replication. On to, I guess, if we have any time left. Yeah, we have about 3 minutes left. Yeah, okay, just enough time to start to talk about consensus a little bit. So I would be lax if I didn't mention the Raft paper. So here's the paper on the Raft consensus algorithm, which came out in 2014. This is the long version, which is, I think, longer than the version that appeared at ATC. So I think what's interesting as you look at this paper is, so, I mean, there's a couple things about it that are interesting. You know, they emphasize understandability of the algorithm versus Paxos. And they actually go to the trouble of having a user study in this paper where they ask people questions about both Paxos and Raft and ask them, you know, which is easier to understand? Right up front, they acknowledge their debt to previous work. And one of the particular things that they emphasize that their work is similar to is the work on view-stamped replication, which we briefly mentioned. So I thought I would mention this paper as well. Note here that right in the title, they call this a primary copy method or a primary backup method. So what's interesting here, right, is it's like, well, I told you view-stamped replication was a consensus protocol, but they're saying that this is a replication strategy right here. And so, well, aren't those different things? And so again, I would go back to what I said at the beginning of class, and I'd say they're not that different, right? Because so what they do in this paper is present a replication strategy and then point out that you need to have consensus in order to make this replication strategy work. And the core idea of view-stamped replication is that consensus protocol that they came up with. So once again, it's Barbara Liskov who was the primary investigator on this work. Brian Oki was her student, and I think he's at Microsoft Research now, continuing to do awesome work. I could be wrong. I can't remember if it's him that's at OSR or somebody else. One thing that's interesting about both this and Raft is that they don't set out to say so much like, we're going to do a consensus algorithm. They set out to say, we want to do replication. In order to do replication, we need consensus. And so we're going to tailor our consensus protocol and everything about it to the particular use case of needing to do replication. And so unlike Paxos, right, where with Paxos, you have to extend it to multi-Paxos and you have to do certain optimizations and so on in order to make it suitable for this setting of replication. With these things, they just assume that replication is the thing that you want to do right from the start. And these different consensus protocols, they turn out to have a lot in common. I think I mentioned this paper briefly in class, this paper that contrasts Paxos and view stamped replication and ZAB, the Zookeeper Atomic Broadcast Protocol, which we briefly talked about. So this paper points out their similarities and differences, but they really do all have a lot in common. And what I found, the feature of this paper that I liked the most is that there's a table in here that's almost like a Rosetta Stone of terminology right here. So at the top of this page, translation between terms used in this paper and the various replication protocols under consideration. So they're contrasting Paxos, VSR, and ZAB, and they're for every one of these terms, like you see Paxos, there's like learner, acceptor, leader. They talk about how in each of these other systems, there's the same concept, but under a different name. And so when I first looked at this paper and I flipped the page to this table, I actually gasped because it's so interesting to me that all of these people ended up with very similar ideas, but going by different names. Very common in computer science, but this table really lays it out very starkly. And of course, not all of the ideas are in all of these systems, but I think it's really fascinating. And then if you can read this paper, you can read this paper in much more depth to get a clearer idea of the differences. And very recently, Heidi Howard and Richard Mortier wrote a paper about comparing Paxos and Raft and just kind of saying, like, are they really so different after all? And what they end up doing is describing a simplified version of Paxos using the terminology of Raft. So in this paper, this Van Rennes and Schneider paper, they talked about Paxos, VSR, and ZAB. They didn't even talk about Raft at all. It was actually kind of throwing shade on Raft that they didn't talk about it because Raft had just recently come out and was very popular. But this paper actually compares Paxos and Raft directly, uses Raft terminology to talk about Paxos. It ends up showing that Paxos and Raft aren't that different. And the popularity of Raft can largely be attributed to the fact that it is easier to understand, and there's this nice paper that it makes it quite straightforward to implement Raft from the paper, as opposed to Paxos, which is very hard to implement from a paper. So that's it. That's our tour through the last several decades of we only scratched the surface, but there's several decades of papers in distributed systems that I thought I would mention to you. We looked at like 16 or so. I can share the links later if you're interested, but that's it for today. We will see you next time for our guest speaker, Carissa McKelvey, and take care of yourselves. Bye.